So CMOS divider, single divider, my conclusion is that I don't recommend, do not use it. If you want to use it, just use a static logic. If you want to design any divider for product, use a static logic. If you want to use the dynamic logic, yeah, true single phase clock logic is most reliable one because you don't need a clock bar. But still, dynamic logic means that the operation frequency is extremely sensitive to the voltage variation and temperature variation. And also there's a minimum frequency to maximum frequency range. Static means that nearly DC to maximum frequency. So all you have to do is that check the maximum frequency and you don't have to check the low frequency. But dynamic logic means that you have to carefully check the maximum to minimum range. And this one, time window, frequency window, change a lot over PVT variation. So I don't recommend this one. And other reason is that the VCO and divider prescaler cannot be very far away because otherwise you have long metal routing. So this capacitive loading also will hurt the input, speed. So this can be close to the VCO, then this digital logic working at 2 gigahertz or 1.5 gigahertz means that this one creates a large amount of LDITT noise, switching noise. So this one will be kickback to VCO. So this divider noise may be affecting and making a noise, switching noise coupling to the VCO. So I suggest that for real product level design, I always think that prescaler must be designed in CML, differential logic. So this is my suggestion. So now current mode logic is just normal 2 master slave latch will form the flip-flop. So this is the latch one, very similar to some computer design, right? We have preamplifier and latch. So now with the clock is high, and this one will be a latch transparent, and then the clock is low, this one will be turned off, and then now this one will be governed by this positive feedback system to hold the state. So this is what, and then even CML divider, the good thing is that you can even embed the logic. So modulus controller, we need the AND gate that can be further included. And then in CML design, do not worry too much about the triode region. Even though this one, you have a large swing, this one can momentarily enter the triode region, but CMOS is fast enough compared with the bipolar. You don't have to worry about the transition between the linear mode and saturation mode. So it is okay to be momentarily in the triode region. More important part is that you should guarantee that this current meter must be always in saturation mode. This is more important. Otherwise, this one become enter the triode region. Actually, this one current will dependent on the supply voltage. Then now when the current value changes, now important part is that the common mode voltage will change. Once common mode voltage change, this node will go to the next stage, clock. Then this voltage going reduced. Then this VGS drop. Then this will choke the current meter. Then this one will become also triode region. So this supposed to 100 microamp, but because triode region, maybe this one may be only 70 microamp, then this one may not even work properly. So this is very important. So design aspect of the CML divider, one of the big difference between the university paper and industry product is that maybe you can expect maybe 3 or 4 times higher power consumption than the paper, or sometimes more than 5 times. The reason is that university paper does not consider too much about the input sensitivity. So mostly they tend to use the small swing with a small W ratio, and then that means that it doesn't have a complete switching. So current mode logic means that this is the static logic. This is not a dynamic logic, meaning that when we have input state, you have to guarantee that actually, ideally 100% must go high when this is high, and 0% current is going here. But when you have a small signal swing with a minimum W ratio, then actually this swing is given by the square root times 2 VDS set is the guaranteed swing. Actually, we need more than this number. But anyhow, this one, as you know, is the overdrive voltage, right? This is 2I times VDS over mu Cox and the W ratio. So that means that if you use small W ratio, actually that, and then with a small swing, that means that maybe you cannot never guarantee that this one can be fully switched. Maybe when clock is high, maybe 60% current going here, but maybe still 40% will go here. This is very dangerous. So when you have a small signal swing, actually looks like a dynamic logic. You need to find some sweet spot of operating range with the minimum power, but this is not good because this is highly sensitive to the temperature variation. So you must guarantee the good input sensitivity, and the input sensitivity is coming from large W ratio or the small current. So when you increase, for example, increase supply the bias current for the given W ratio, actually input sensitivity becomes worse. So you must increase the W ratio. Once you increase W ratio, this one will increase the loading capacitance to the previous state. So there are many things to be considered for the CML divider. And then so that's why the one of the most critical parameter is the voltage swing. How to set the IB times RL. So this one you set the common mode voltage first. It should not be too low. Then this low voltage will affect the next stage. This one will go to the gate. And then now VGS and then this current meter in the following stage will be suffered. So and then when you have increased the current, also this sensitivity will be worse. So this is a very important part. So V-swing, low V-swing is not suggested. And then do not worry too much about saturation mode like ECL. So do not never ever put the level shifter like a source follower, like emitter coupled logic, because in CMOS source follower is not good for high speed design. So usually speed is worst with a hot temperature and slow corner. So because of high R with a slow corner and the low mobility, so this will give the lowest speed. But sensitivity might be worst for the fast corner, because fast corner means that resistor R is smaller and hot temperature means mobility is low. So then this one doesn't have enough gain. So now sensitivity might be worse. So if you don't have time to check all 9 corner or 10 corner condition, you must at least check 2 corners, fast hot and the slow hot corner. If you can guarantee the function with these 2 corners, other corners are mostly okay. So these 2 corners are very important. And never ever get tempted to use small SW. Once you have an input sensitivity issue, maybe this one cannot flip error. So divider cannot work error. And once this one, you have a problem, because this is caused by W ratio as well. So simply increasing the current or increasing the supply voltage may not help much to solve the problem. Then divider doesn't work, your PLL will be dead, and this is a very serious problem. Okay, I have some questions, but out of time, so maybe I'm not sure. So first, let me finish this part quickly, and then let's see. So, and then one tip is that's why I also university paper never put the input buffer for product level design. I strongly suggest that you have to put the input buffer. In that way, the divider can be a little bit far away from the VCO. And secondly, normally, so never ever simulate the divider with ideal sinusoidal source. You must always put the ideal sinusoidal source here and the VCO buffer and then some parasitic capacitance, and you must put another input buffer. So why? Because input sensitivity means large swing, but another important part is that this slope, rising falling time. Even though you have a large swing, but it's a smooth, like a triangular shape, then deep flip-flop will not work, because during this time we have a huge overlap with the clock and clock bar, and this overlap time, during this time, current will flow in the both sides, clock and clock bar with a significant portion, and then the positive feedback will not work. So that's why smooth condition is the most dangerous part. So from sinusoidal, if you have long routing, it's very likely that you will have a reduced area, but also you will have the reduced slope. Then you must recover this one. So that's one way is that you have the input buffer with some gain of maybe more than 2. This one can boost the rising falling slope. Then that will work properly. So in the way, actually your prescaler design can be decoupled to the other condition much. So you don't have to worry too much. And then you can fully focus on this one. But if you this is designed by design A, this is done by the design B, and then both of them are okay because he designed with some just ideal sinusoidal source and then guaranteed to satisfy the design specification. But on the top level, now if this kind of situation occurs, this is the most dangerous situation. Then PLL cannot work because feedback divider doesn't work. You cannot even test the PLL except the open loop VCO. So this is the most dangerous scenario. So for product level design, I strongly suggest that you put the input buffer all the time at the cost of the power consumption. So aspects of the divider chain, I already mentioned it. Once you touch some part, don't forget it will affect everything. For example, you increase the current, this will affect the DC operating point. And then once you increase current, input sensitivity will be worse. Then you must so increase current and reduce the resistor. So because RC time constant will limit the speed of the divider. So the best way to improve the speed is to increase the current and reduce the resistor, that you can see the immediate improvement in the speed. But what you lose is the sensitivity. Again, sensitivity is given by the square root IB over WL. So now IB increases, then minimum delta V to fully turn on the differential pair will be increased. So that means that to compensate for this increment, you must increase the WL. But once you increase this WL, this COX, gate oxide capacitance will increase. So you must still have reduced the speed. So then you must reduce the R by increasing I, then this will affect. So this one all will propagate. So you have to be careful. And other thing I suggest is that some of you design, junior engineer design with a longer L, because you learn that column mirror should have a longer L, but don't forget, CML divider is the static logic. The main purpose is just logic function, and it is well known that the matching and noise performance of the divider is not so critical. Even you have a full matching, maybe several percentage. Actually, it's difficult to have more than 10% mismatching for the normal layout. Anyway, let's assume that even few percent matching doesn't matter. So do not use the wide metal to get the better matching like some ADC or the reference circuit design. You use the minimum width because this plastic capacitance is more important. You must use the minimum width with a small area, and then you must use P-poly, because P-poly has the higher density than M-poly. So P-poly resistor and matching is not so critical. And here, not entering the triode region is much more important than the like channel length modulation effect. So what you can do is that you reduce the L a lot. Do not use 1 micrometer, 2 micro, just to maybe 0.1 micro or 1 nanometer, and then increase the W a lot. You have a large W ratio, so that this can work as a sub-threshold region, and it can never enter the triode region. So that's the one tip for the CML divider, because divider itself does not add noise much to the PLL. Actually, if you have a problem of the noise, it's mostly come from the 90% come from the VCO, maybe another percentage maybe come from the charge pump. And the layout is very critical. So my recommendation is that, again, first, it is, as you know, you must use the large number of fingers for critical circuit. So, for example, this portion is important to switching circuit. So you need to, if you have a 10 micro, you must use maybe less than maybe 0.5 micro times 20 fingers. So you need a large number of fingers to minimize the parasitic capacitance of the drain part. So small W with a large number of fingers is important because this is minimum L. So even though you have a large L, this total width will not increase too much. But bias, again, bias cannot be minimum L, still maybe 100 nanometer or something. Then even if you use a large number of fingers like this cell, then this area will increase. The width of the layout will increase a lot. The problem is that this is the critical node. So this is the critical node. So it's the same color. So this is the critical node. So this there will be another CML divider here. So one good strategy is that you need to make a tall, very tall and thin CML divider here. So this is divided by 2, And next following divider, cascade divider 2 is very tall and thin, so that this line can be minimized. From divide by 2 to the next clock, this line can be shortened. So this is very important. So how to make it tall and thin? First, this is the critical path point. You have to minimize the plastic capacitance. When you have a large, sometimes you have a large resistor, sometimes you have a small resistor. Regardless of this one, do not align this part. You must align this part, and this one can be extended if you have large R, and then this size can be large, but this part is not critical. You must minimize this area, and then bias. You can use a large W is okay. So do not use the minimum W because the bias, even long W doesn't matter for the speed error. So this capacitance is not critical. So you can use long W because L is already high. So they try to match the total width. So then you can have a tall and thin and cascade it, and you can minimize the one. So this is the example of the old layout by some my previous student. So he designed the CML like a digital logic. He designed the layout one by one. 8 GHz toggle flip-flop, 4 GHz toggle flip-flop, and sometimes he rotate and even buffer. So this yellow is the critical path. You see it's going up and down because he just do it in his own way, like a digital cell. But now after same circuit, we did the layout again. As I said, we did it this way. So we do like a long bias pipe and this, and then we do some additional capacitor and the gate source capacitance. And then, but key part is the critical path is all well aligned. And this is a resistor. So low power CML, we need a small I with a high R. So R will increase, but we extend this way. But this portion can be always minimized. In this way, without changing the circuit, by using the layout, still we can reduce the power a lot, and then it's become very compact now. And then more important part is the critical path has been significantly reduced with almost a straight line. So this is the one important design aspect for the CML divider.